This is the next lecture in number theory. Last time we talked about the integers and how the integers are the unique well-ordered ring where the ordering respects addition and multiplication. This time I want to talk about the so-called division algorithm and the Euclidean algorithm. And yeah, so this is what I want to talk about. So let's just start off with what the division algorithm is. So when I say division algorithm, well, if you remember back to primary school, if you look at 7 and you divide it by 3, well, this is 2, and then you have this 1 left over. And then later on we said, well, you could take this 1, and this is a repeating decimal, 2.333 repeating. But that's not what we want. That's what we did when we learned decimals. But before that, we would say this 7 divided by 3 is 2 with remainder 1. And that is exactly what the division algorithm says and how we will be using it. But how do we know this works? So let me tell you what the division algorithm is. So given integers a and b, and b can't be 0, because because you can't divide by 0, then there exists integers q and r such that a is equal to bq plus r, with r is strictly between 0 and, well, r is either 0 or it's less than b. And so this is what the division algorithm says. And furthermore, we'll say it's a unique. So this exclamation point after the E says there exists unique integers q and r. So let's go ahead and prove this. So there's two things. First, we have the existence of q and r, and then the uniqueness. So to do this, let us consider the set of a minus bq such that q is an integer, and a minus bq is greater than or equal to 0. So let's call this set x. So by the well-ordering principle, x has a smallest element, or yes. So this is a subset of the positive integers, because a, b, and q are all integers, so this is a set of integers. But there's one caveat here. We need to observe that this set is not empty. So note X is not empty. Say if A is positive, take Q equal to 0, then A minus BQ is greater than or equal to 0. If A is less than 0, or you could also, I guess this is greater than or equal to 0. If A is less than 0, well, then you can take Q to be plus or minus A, so that A minus BQ is just A times 1 minus B, and this will be plus or minus B, depending on if you choose Q to be plus or minus A, but you'll just choose whichever value that will make this. We know B is not 0, so you can just choose the value here that makes this not positive, because this is not, since A is not positive, you can choose this so that plus or minus 1 plus or minus B is not positive, so negative, and the product will then be positive. So this set is non-empty, and we have a smallest element R. Now, let Q be, so let Q and Z be such that A minus BQ is equal to R, and namely, A is BQ plus R, which is what we want, but we also have that, what else do we have here? So A is BQ plus R. We claim that R is between 0 and B. So if not, we know R is greater than 0. If not, then R is bigger than B, right? And what we could do is, we know that, so this means, so R minus B is positive. Then A is equal to B times Q plus 1 plus R minus B. So R minus B is in the set X, because namely, I should say greater than or equal to 0. This should be greater than or equal to. So R minus B is in X, but this contradicts that R is the smallest element of X. So from this, we conclude that R is between 0 and B. So that gives us the existence of such a Q in R. So the next part we have to do is the uniqueness. So how can we do the uniqueness? Well, so say we have A is BQ plus R, and A is BQ prime plus R prime, with the R's strictly less than or equal to B, or that should be that, and all of these are integers. So we want to show that Q equals Q prime and R equals R prime. That's what we want to show. So what we can do is, well, we know A is BQ plus R, but it's also BQ prime plus R prime. So we know BQ plus R is equal to BQ prime plus R prime. And this tells us that B times Q minus Q prime is equal to R prime minus R. What does this tell us? This tells us that B divides R prime minus R. And let's just say that, let's say R prime is greater than or equal to R. So this is positive. So without loss of generality, we can make this assumption. So B divides this number, right? So, and that just means B, R prime minus R is B times something. But we know, since so we have 0 is less than or equal to R, which is less than or equal to R prime, which is less than B. If we subtract R from all of this, this tells us that R prime minus R is strictly less than B. R prime minus R is going to be less than or equal to B. Why is this true? Because, well, R prime is less than B, and we're just subtracting something positive. And it's also greater than or equal to 0. So we know R prime minus R is between 0 and B. But since B divides this number, that implies, well, what are the multiples of B? The multiples of B are 0, plus or minus B, plus or minus 2B, and so on. But none of these multiples are strictly between 0 and B, so that implies that R prime minus R is 0, and since B is not equal to 0, that also tells us Q minus Q prime is equal to 0, or R equals R prime and Q equals Q prime. So this is how we can get uniqueness from the Euclid or division algorithm. So yeah, that is the division algorithm. And so maybe I should define what it means. For A and B to be integers, A divides B, and we would say A divides B. This means that B is equal to A times X for some integer X. Alright, so we have the division algorithm, and now we can talk about divisors, or greatest common divisors. So given a and b integers, the greatest common divisor of a and b is the largest element c, such that c divides a and c divides b. So let's figure out what do I mean when I say largest C. How do I know that there is a largest? Well, we always know one divides A and one always divides B. So the greatest common divisor is always greater than or equal to 1. So it's always going to be positive. Also, we know that if you look, A divides A, since A is equal to A times 1. And we have no other larger divisor. Since if you had a larger divisor, say, and let's just assume A is positive, because you can also always multiply by -1. If you had A is equal to B times X for some B that's bigger than A, we'd have to have X is positive as well. But so X is greater than or equal to 1, but then this right-hand side strictly bigger than the left-hand side, because it's something bigger than 1 multiplied by something bigger than A. So we have that A is an upper bound for the GCD of A and B. So we have that this upper bound, so if you consider the set of common divisors, it is bounded above by A and B, either or. So we have that there will be a largest element. So a question comes, how can we compute the GCD? And this is going to be the so-called the Euclidean algorithm, which says if you have A and B are integers, and say B is not 0, and let's say A is bigger than B, then the GCD of A and B is equal to the GCD of B and R, where R is given from the division algorithm. That is, A is BQ plus R. So the GCD of A and B is the same as the GCD of B and R. So let's go ahead and prove this. So first, say C is the GCD of A and B, right? So C is the greatest common divisor. So A is C times X, and we can write B is C times Y. then we have that if you look at A as BQ plus R, then we can say this is CX is CYQ plus R. So we have that R is C times X minus YQ. So we have that C divides R. So we know that the greatest common divisor of A and B will also divide R. Similarly, let's say D is the GCD of B and R. So let's write B is RM and B is dm, R is dn, then A is dmq plus dn, which is dmq plus n. So D will divide A. So what we have just shown, we have shown that the GCD of A and B, this divides it divides R, but it also divides B. So namely, this will divide, so this tells us that the GCD of A and B divides the GCD of B and R. Similarly, if we consider the GCD of B and R, this divides both B and A, so the GCD of B and R divides the GCD of A and B. So, what we've just shown, what does this mean? So, and remember, so our claim is that if C divides D and D divides C, and let's just say we know they're both positive, then I claim that C is equal to D. And this will give us the claim, because we'd have that this GCD divides this GCD divides that, and they're both positive, so that would give it to us. So what does this mean? Well, since C divides D, we have C is equal to D times X, but similarly, we also have D is equal to C times Y. So, if we plug this expression in here, we have that C is equal to C times XY. So, X times Y is equal to 1. And if we think about the integers, so in the integers, if you have two things that multiply together to give you 1, so then they're either both -1 or they're both +1. But since we assumed everything's positive, this has to be 1. And the reason being, so we could have claim in Z, if we have X and Y are greater than 0, and XY equals 1, then X equals Y equals 1. Well, the reason being behind this is we note that, so we saw that there's no integer between 0 and 1. So that tells us that x and y are both greater than or equal to 1. But if either was greater than 1, then the product has to be larger. So say we have 1 is less than or equal to x. And so assume for contradiction that we had one of these were not 1. So, and let's say it's larger. So y is bigger than x. And or they could be equal, but y is not equal to 1. So what we know is we want to show xy is greater than or equal to 1, which is the same as saying xy minus 1 is positive, and we know y minus x is positive or 0. Oh, and now let's just multiply this whole thing by x. So we have xy minus x squared is greater than or equal to 0. And we note that x squared is greater than or equal to 1, because 1 is less than or equal to x. So this tells us that xy minus 1 is greater than or equal to 0. Or I guess strictly greater than, because y is not equal to 1. So what I'm trying to say is the fact that xy, the only things with multiplicative inverses in the integers are 1 and negative 1. And since xy is equal to 1, you have that x equals y equals 1 because we assumed they're positive. And this tells us the so-called Euclidean algorithm. But this isn't the whole story, because here I assumed that b is not equal to 0. So what is the greatest common divisor between a and 0? I claim this is a. And the reason being is we know a divides a, and a also divides 0, since 0 is equal to a times 0. So, and we saw a is the largest element that can divide a. So we have this GCD as a. So, namely, we can do the step, go a step further. So what we can do is we can say, if we have a is equal to b q1 plus r1, then we can do b is r1 q2 plus r2, and then r1 is going to be r2 times q3 plus r3, and if we keep going, at some point we will have a remainder 0. And so it will have, like, say, Rn minus 1 is equal to Rn plus Qn plus 1. and plus 0. And you can think of this 0 here as, say, Rn plus 1. But it's not here. And so when you keep repeating this, there are two claims, namely, this process terminates, and the last claim is that the last non-zero remainder, so up here we'll have Rn minus 2 is Rn minus, or no, Rn minus 2 is Rn minus 1 plus Q times Qn plus Rn. So the last non-zero remainder is the GCD of A and B. So how can we do this? So first off, I'm going to prove something. I like to call it the 2 out of 3 principle. And namely, if we have an expression like A equals B plus C, if we have some x, if x divides 2 out of 3 of A, B, and C, then it divides all 3. And the proof of this is simple, because if x divides B and x divides C, you just factor out the x, and then you get that x divides A. And so I'll just state it. And if x divides A and x divides B or C, you move the B to the other side, factor out the x, and then you have x divides C. So to get that Rn is the GCD of A and B, we know, just looking at this, we have here that the GCD of A and B, well, this is the GCD of B and R1. And here, the GCD of B and R1 is the GCD of R1 and R2. And if we keep continuing this, when we get down here, we're going to see that the GCD of, so if we go to this guy, so namely the GCD of this and this is equal to the GCD of this and this. So if we look at it down here, oh, and this here should have been a multiplication. So if we apply that down here, we'll see that the GCD of Rn minus 1 in Rn is equal to the GCD of Rn and 0. So GCD of Rn minus 1 in Rn is equal to the GCD of Rn and 0. But we saw up here that the GCD of anything in 0 is itself. So this is Rn. So if you just continue the string of equalities going up, you have that the last non-zero remainder is the greatest common divisor. So that's one part of it. So we have that Rn is the GCD of A and B. But the other part that we need is, why does this process terminate? So how do we know this process will actually finish going? So that's just noting the following. Since A is BQ, well, we know that each of the non-zero, so we know b is less than r1, this is less than r2, this is less than r3, and so on, and all of these are greater than or equal to 0. So if this process did not terminate, then we would have a sequence of strictly decreasing integers, positive integers. But that's not true, because we have just take the first b of these and you would have had to reach 0. So that tells us that this process terminates, and furthermore, the last non-zero remainder is the GCD. So that's the Euclidean algorithm, but there's also an extended version, which says that there exist integers m and n such that the GCD of a and b is equal to m times a plus n times b. And kind of a proof of this is doing a back substitution. So if we look at this here, so maybe I will copy Is there a way I can paste? Yeah. The idea behind this is we have this equation here. And we can rewrite this equation as Rn is equal to Rn minus 2 minus Rn minus 1 Qn. And above this equation, so kind of above here, we have Rn minus 3 is Rn minus 2 Qn minus 1 plus Rn minus 1. So that's kind of the equation that comes before this. So what we can do is we can rewrite this as Rn minus 1 is Rn minus 3 minus Rn minus 2 Qn minus 1. And we can take this here, plug it into this equation, and that gives us an expression for Rn as a factor of Rn minus 2 multiplied by Rn minus 1. And you can just keep going up. So more generally, we have Rk is equal to Rk minus 1 times Qk plus Rk. So this tells us that we know R sub k is equal to R sub k minus 2 minus R sub k minus 1 times Q sub k. And to make this simpler, because we also want to include a and b at the very end, let's call b R sub 0 and a R sub negative 1. So we want to show that Rn is equal to sum a times R of negative 1 plus b times R 0. That's our goal. And so what we can do is we can kind of do the well-ordering principle, I think. So if we consider X, it's going to be the set of indexes K. K greater than or equal to negative 1, and such that So we have the set of indexes where r sub n can be written as a times r sub k plus b times r sub k plus 1 for some integers a and b. And the well-ordering principle says this has at least elements if it is non-empty. So let us assume for sake of contradiction. So if this set x is empty, so our goal is x is the empty set, so there is no element k that's greater than or equal to -1 such that this statement fails, because that would tell us that we can write Rn as, oh, and maybe I shouldn't have used a and b here. Maybe I should have used m and n, because a and b are r-1 and r0. So if we assume for sake of contradiction that x is not the empty set, then let k be the smallest element. Or, is that how we want this to work? Or we could do the largest element, because this is the set of k between 0 and n. Because if we pick the smallest element, if the smallest element's -1, then that won't work. Okay. Because we're kind of going backwards here, because we're starting at k and moving backwards. So maybe what the set should be is the indices. Well, I guess this is less than n. Oh, I should do not equal to here. Because if x is the empty set, then every Rn is equal to mRk plus nRk plus 1. So if we take the smallest index to do how do we formalize this? If we take the smallest index and x is the smallest index, then if the smallest index is 1, okay, maybe we want to pick the largest index. And we know it's largest because this is a finite set. So we'll note that n is not in x, n minus 1 is not in x, let's just say n minus 2 is not an x as well. Because we saw up here Rn is Rn minus 2 minus Rn minus 1 times Qn. And similarly, we writing Rn minus 3 and plugging this in here gives us that Rn minus 2 and Rn minus 1. So if you take the largest index k, we note k plus 1 and k plus 2 are less than or equal to n. So we know Rn is going to be something is m times r sub k plus 1 plus n times r sub k plus 2. But we can also write, we know r sub k we know that r sub k plus 2, so r sub k is equal to r sub k plus 1 times q sub k plus 2 plus r sub k plus 2. So this tells us r sub k is equal to r sub k plus 2, or r sub k plus 2 is equal to r sub k minus r sub k plus 1 times q sub k plus 2. And if we plug this in here, this tells us that r sub n is m r sub k plus 1 plus n r sub k minus r sub k plus 1 q sub k plus 2, and just rearranging terms, this is n times r sub k plus r sub k plus 1 m minus nq sub k plus 2. But this implies that r sub k is in X, contradicting it being the largest element. And so we conclude that this set is empty, and the GCD of A and B can be written as a integral combination of A and B. Now, I don't. This works, and you can back substitute, but I like doing something else. So what I learned was kind of, so say we have two numbers. Say, I'm trying to think, we have 12 and and 39. So classically, how you could do this is you can say, okay, 39 is equal to 3 times 12 plus 3, and then 12 is equal to 3 times 4 plus 0. So this tells us that 3 is the GCD of 12 and 39. And furthermore, what you can do is you can take this equation here, and you can say, well, 39 minus 3 times 12 is equal to 3. Okay, maybe this is a bad if we do 5 and 8, so their GCD is going to be 1. So this is kind of just doing it in one step, so it's pretty easy. But if you want to do 5 and 8, you would say, well, 8 is equal to 5 plus 3, 5 is equal to 3 plus 2, 3 is equal to 2 plus 1, 2 is equal to 2 times 1 plus 0. So that tells you 1 is the GCD, and then you have to take this and say 1 is 3 minus 2, and then you say this is 1 is 3 minus, well, 2 is just 5 minus 3. And then you'd say, well, so this is actually saying 2 times 3 minus 5. So that's using this. And then you'd use this last one and say, well, 1 isn't actually 3. Or 3 is actually 8 minus 5. And so this would give us 1 is 2 times 8 minus 3 times 5. And this is how you could do it. And there's nothing wrong with doing back substitution, except it's a little tedious. And the way I learned to do it, or one way, is to make the following table. And so if we want the GCD of 8 and 5, well, we're going to think of this top column as our 8's column and this right column as our 5's column. So currently what this table what this first row of the table says is this just says 8 is equal to 1 times 8 plus 0 times 5. And this says 5 is equal to 0 times 8 plus 1 times 5, which are very true and easy to see statements. So the way you go from here to get the next element of the table is what is the remainder. So if we looked at 8 and 5, right, its remainder was 3. And how did we get 3? Well, we got 3 by subtracting 5 from 8. So what happens here, you would get a minus 1, because we subtracted 5. But say this was like a 10, or if we did like, if this was 11 and 5, what would happen is since 5 goes into it twice, you would subtract 2 of this second column from this first column, and you get 1 is, yeah, so the last non-zero element is your GCD, and these entries here give you the combination. So 11 minus 2 times 5 is 1. So continuing up here, 3 goes into that once, and with remainder 2. So we have to subtract 1 of this row from this row, so we get a minus 1 and a 2. And then, let me move this down. And then 2 goes into here once, so you subtract it, and you're going to get a 2 and a minus 3. So here you say that 1 is equal to 2 times 8 minus 3 times 5. Here you say 1 is 11 minus 2 times 5. So yeah. Maybe, so if we did like 8 and 3, I think this has a couple of steps that are different. So what you could do here is 3 goes into 8 twice with remainder 2. So you subtract 2 from here, 2 of the second row from the first row, and then 2 goes into 3 once. So you subtract 1 of the third row from the second row, and you get 1. minus 2, and 3. So this here tells you that 1 is equal to, no, we subtracted 1 of this from this. So this becomes negative 1, that's 3. So it tells you that 1 is equal to negative 8 plus 3 times 3. And so, yeah, that's how I tend to calculate or do the Euclidean algorithm. Plus, I feel like this is a much more simpler way to implement the Euclidean algorithm in a program, because rather than doing all this work of back substituting, you can just make an array and you just update the array as you go along, and it's a bit easier of an implementation. So yeah, that's about it for the division algorithm and Euclidean algorithm, extended Euclidean algorithm.